Hello. I'm going to talk to you about interpreting Liquidus surface projections in ternary phase diagrams. A lot of people don't like these because they think they're quite complicated, but actually they're not. So this is the Greek alphabet and it's useful to know it. We tend to use the small letters only, the lowercase if you like. Uppercase get used for all sorts of other things. So we use the small letters only, and we use these to denote some of the solid phases. And it's worthwhile getting to know them, or at least recognizing what they are, and then being able to look them up. I've put this in. This is a phase. This is defining the phase rule, and the proper phase rule is this. But we, as metallurgists, often use the condensed rule. Instead of having a 2 there, we have a 1 there. And the reason we can get away with that is because most of the time we can assume that the pressure is atmospheric. If you're a geologist, you can't do that. And then I'm assuming that you're familiar with a binary eutectic. So we have the liquid line there, and we have the solid line, sorry, the Liquidus line there, and the Solidus line there. Everything above the Liquidus is liquid. Everything below the Solidus is solid. So between the two, we have liquid plus solid regions. And then the Liquidus lines tell us what it's going to solidify to first. So in binaries, we don't really think about this too much, but this, anything on there will solidify to alpha first, and anything on there will solidify to beta first. I'm stressing that because it's important later on. So for a binary where our number of components is 2, when there's no degrees of freedom, i.e. it's an invariant reaction, that's when we have 3 components. So for this invariant reaction, which is the eutectic reaction, we've got alpha of that composition, liquid of that composition, and beta of that composition at that temperature, which is an invariant reaction. So when we go into having a ternary phase diagrams, it gets a little bit more complicated. With a binary, there's 2 components. With a ternary, there's 3 components. So binaries can very easily be 2-dimensional, and ternaries have to be 3-dimensional. So that's less easy to view on the screen or on paper as the binaries are. So therefore, we need sections or projections to cope with being able to see them clearly. So we need to learn about those. And in a binary, we get single or 2-phase regions. And if you have 3 phases, that's the maximum you can get in a binary. That's in an invariant reaction, and it's a horizontal straight line. We've just looked at one on the binary eutectic. In the ternary, we have single, 2-phase, and 3-phase regions. And when you've got an invariant reaction, that's 4 phases, and that's on a horizontal plane. So it's more complex. So what did we do? For a binary, it was easy. We had composition along the bottom and temperature up on the y-axis. We've still got temperature up on the y-axis, but now, instead of a line going across like a binary, we've got a composition grid because we've got 3 components, A and B and C. So now we've got this composition grid because we've got 1 more degree of freedom having 3 components instead of 2. And how do you read this thing? Well, you start off with the element that you're interested in, you go to the other side, and then you count back towards it. So this is 20% A, and you go to the other side for B, and you count up 10, 20, 30, 40, 50, 50% B. Now you could add up your A and B and take that away from 100, and you'd know that it's 30% C. But I always like to check, because sometimes you make a silly mistake and then you can waste time trying to sort it out. So C, we go to the other side and we count back towards it, 10, 20, 30. So that's the composition. And then I just gave another one here for an example. So that's the composition grid. This looks totally horrible, and this is the space diagram of the iron, chromium, and carbons over there somewhere. And it looks really horrible, partly because it's a very old diagram and it's a photocopy of a photocopy. I really must try and get another version of it, but it's just too complicated. You might recognize the iron-carbon diagram here. You might recognize carbon-iron there, but you don't know how far back to go. Okay, so because that's really complicated to interpret, and if I start saying, oh, 50% that and 10% that and whatever, it's very difficult for you to follow in there. It's very difficult for me to follow. So what we do is instead we take sections of that or projections to put it into 2 dimensions and make it easy to see on a paper or on the screen. So what we're going to be looking at in this one is a projection of the Liquidus surface. So here's the Liquidus surface. You can sort of see what's going on because everything is underneath it, and we would project that down. So imagine having a little light bulb up here and projecting just this surface, which actually is lots of little surfaces stuck together, and ignoring what's underneath it. And that's our Liquidus surface, okay? This just breaks up things again. So the space diagram is the whole lot. It's in black. It's everything, okay? But it's very difficult to interpret. The Liquidus surface is looking down on it and projecting that. And then isothermal section, I've done in another talk. Vertical section, I'm not going to do because I don't like them. And basically that's what its name is. It's got other names as well, like isopleth. It's a vertical section through the space diagram. And there's an example there. Now, mathematically, it's correct. But as you'll see in the talk on isothermal sections, the tie lines after the Liquidus surface, anything under there is a bit of an approximation what is actually going to happen, because the tie lines are unlikely to lie in that vertical plane, not all of them. Okay, we're not interested in that. We're interested in the Liquidus surface projection, where you're looking down on this and just projecting those surfaces. And it's a very useful diagram, okay? That's why I'm going through it. So in diagram, well, let's go back. In this diagram, we're interested in all the components equally. So it's plotted as an equilateral triangle. Don't worry if you can't understand that too much. I'm going to be unpacking it. This is just an example. Okay, so for diagrams where there's a major component that you're interested in, and you're not really interested in very much of one of the components, they tend to get drawn as a right-angled triangle. And here's an example. So we've got iron is the one that we're really interested in. Chromium, we do go up to 100%. And if you look along here, carbon only goes up to 15 weight% because we're not interested in that. And even here, they haven't even drawn all of it because nobody's really interested in that. And here's the Liquidus surface projection, sometimes called the Liquidus surface, sometimes called the Liquidus projection, sometimes called the liquid surface projection. And what it shows is it shows areas where the liquid is going to solidify to a particular phase. So here it's going to solidify to the chromium-rich solid solution, and a little bit of jiggery pokery over there because iron and carbon dissolve in each other, and that's an isomorphous phase diagram across there. So it magically swaps from chromium to delta ferrite over there, but it's basically the same phase, body-centered cubic. It's just that number of atoms is changing, the proportions are changing. Then anything over here will solidify to austenite or gamma iron. Here is chromium 23 C6. Here is chromium 7 C3. That's M7C. This is chromium 3, carbon 2, and this is just carbon, but we're not interested in it. Now, this is a very nice Liquidus surface projection because it's nice and clear, and it's got the arrows on it which show you where the direction with decreasing temperatures, and it's also got isotherms on it. Iso, same, therm, temperature. So you can see decreasing temperature down here, which agrees with your arrows, okay? And you'll notice that every time you've got two surfaces joining on this very nice diagram, not all diagrams do this, which is why I've chosen this one, you've got arrows, and the arrows are doing different things. And these arrows are telling you there's a reaction going in this direction between these two phases and the liquid, okay? And then when the three phases meet, now you've got three solids being involved and a liquid. And if you remember earlier, I said that if you get four phases, that's an invariant reaction. And every place where three surfaces join, that's an invariant reaction. And we'll look at the arrows and what it means, the different arrows, in a minute. And we call this a univariant reaction because as you change the temperature, the composition is fixed. Or if you wanted to change the composition along there, the temperature would be fixed. Here's another example. It looks a bit complicated, but don't worry. And it's been calculated by Pandat. That's a little panda, and they haven't put the arrows on, and they haven't put the temperatures on here, probably because it would just get so difficult to read. So I put some arrows on. So I know that's a maximum here between these two pretty high temperature phases that are being formed underneath, and it's running away in different directions. And I know that the temperature decreases down there. In fact, it decreases down to the corner. Okay, so we call these different surfaces, we call them primary surfaces because they are defining the primary phases, i.e. the phases which are going to form first. So anything sitting here within the boundary of this, where if the composition is sitting within that region, it's on the Liquidus surface of cobalt-2, tin, titanium, and it will form that phase first. Now, once you get the hang of this, you can actually have a pretty good stab of what's going to form next, but we'll get there. So we've already defined that. We've already spoken about temperature. I've mentioned the univariant reactions. So there's three phases involved. The univariant reactions occur at the joins between the different Liquidus surface. There's three phases involved, and it's the two solids either side and liquid, okay? And where three surfaces meet, that's when you get a univariant reaction because you've got four phases. You've got the three that meets, and always you've got liquid because it's a Liquidus surface. Okay, and then even if it hasn't got arrows on it, what you can do is you can work out what's going on. Because these, if you look at the isotherms, you'll see it's going down to a lowest point. That tells you it's a ternary eutectic, and I'll show you what that is later, soon. And it's doing the same thing here. This one, it isn't. So it makes it a ternary eutectic. And I've worked out it's a weak ternary eutectic from these lines. So, okay, even though the arrows aren't marked on there, because of these V's, it's very much like a contour map. You know it's going down the V's, okay? It's highly likely to go up. So you can unpack these things. This is a really nice example. It's a bit of a strange one, tellurium, bismuth, and gold, but I like it because it's nice and clear. And So we've got nice clear arrows on, and we've got the isotherms are labeled, which is great. And it's even got the invariant reactions labeled, which are great. And you'll find out that eutectics are called E, and anything else, usually peritectic, is called U. And they start at high temperatures and work down. So U1 is at a higher temperature from U2. You can see this because the arrows are going down, which is higher than U3, which is higher than U4. Okay, this also shows two very special lines, because if you look at this, you'll see that there's a maximum here because these arrows are pointing away from each other. And that means that this is a very special line called an Archimedes line. And we've got another one here where two arrows are pointing away from each other. And we know that's a eutectic because it's a little e. And what it's telling us this is because this is a maximum, it's a very special case where it's acting as an invariant at that point. So liquid of that composition is going to form a phase of maybe not that composition, but not far off, and maybe of that composition, but not far off. It's an invariant reaction. And the same thing here, okay? Very special case. But otherwise, if you do any other vertical section, it'll be much more complicated and it won't be a binary. So because this is acting as a binary, because it's being an invariant, we call it a pseudo-binary. Now, some people call that a quasi-binary. Okay, what's going to happen here? Here is a liquidus surface projection, and here are the three binaries that go with it, and they must be consistent. They must match up. So that's got a eutectic over near gallium, and there it is. Okay, and that temperature must match up, otherwise it's rubbish. This one here has got that high temperature phase there and a lower temperature phase here. Yeah, it's there. This one here has got that very high temperature phase, gallium arsenide, and there it is there. And does the temperature match up? Yes, it does. There's a little eutectic there. There it is. There's the other reactions there. There they are. So what I'm getting across is they've got to be consistent. If they're not consistent, then somebody's made a mistake and it should be corrected. But they should be consistent. And once again, we've got a special case here of the lines going away from each other. So you should be able to join up those two, and that would behave as a binary. So it would be a pseudo binary. This is another example which I like. Again, it's incomplete because the weight percent of carbon only goes up to 7. But we've got the whole load of tungsten this time, and it's got each liquidus surface, okay, named, and it doesn't have the isotherms on. It doesn't have to have the isotherms on, but it's nice if it does. So this is probably an experimental phase diagram, not a calculated one, because with a calculated one, it's easier to get all those isotherms on. Right, and you can see different liquidus surfaces, and where they join, there's always an arrow. This is dotted because they're not quite sure where it is, or dashed rather. So very nice. So in a minute, you will be able to have any composition on here and work out how it solidifies. At the moment, if you just plot on the composition, say we've got 3 weight percent carbon and 40 weight percent tungsten, you know it solidifies to tungsten carbide first because we're sitting on that liquidus surface. And here's some more examples without an isotherm, and here with lots of isotherms, and even you can see the arrows here. This is really quite nice. And then here's another example, and it's another partial because it only goes up to 50 atomic percent. There's the atomic percent written there and there, chromium, and I lie. 60 atomic percent chromium and 60 atomic percent nickel. There's a story why it doesn't go up to that. But what I want to show you is here we've got some ternary phases. And a ternary phase is a phase which has to have all three components in a set way. So we've got these three ternary phases, phi and rho and lambda, and we know they're ternary phases, partly because they don't have a nice binary name like these have got. Okay, remember this shows a solid solution. Alpha, some people reckon there's a different form of chromium, which is beta, but I think that's been shown to be an oxide. Right, so here we know they're ternary because they haven't got nice binary names, but that could be a guess. But you'll notice they don't touch any of the binaries, whereas all the other ones touch the binaries. So this one touches the binary, that touches the binary, these all touch the binary, but not these three. So they're ternary phases. Okay. Right. And you've seen these arrows coming in, and if you're observant, they're doing different things. Okay. And I haven't gone through them yet, but I'm about to now. And I realize that's fallen off the edge. That's a shame. Okay, so the summary of the ternary reactions. If all arrows go in, it's a ternary eutectic. It's liquid plus alpha, sorry, liquid going to alpha plus beta plus gamma, and they call it a class 1. If you've got two arrows going in and one coming out, that's a weak ternary peritectic. So liquid is reacting with alpha and leaving it behind and going to form beta plus gamma. Okay, and the other one, which I've chopped off, is a strong ternary peritectic, which is liquid is reacting with alpha and beta going to form gamma, which isn't there, and that's class 3. And each of these reactions has got their own set of tie triangles. So if we look in here, class 1, it's got 3 binary eutectics, well on this one, binary eutectics coming in together to form a 3-phase solid region. With this one, class 2, it's got 2 reactions coming together above the invariant reaction. And then what you do is you leave a solid 3-phase solid region behind. This one goes off. And then class 1, it's usually a eutectic, and then it splits off to form that phase of that composition, that peritectic phase. And then here's the arrows again. 3 in is class 1, 2 in and 1 out is class 2, 1 in and 2 out is class 3. And here's some microstructures of the different examples. So here, don't worry too much about the particular phases. These are just the average compositions of them. So let's put it into alpha plus beta, or alpha, beta, and gamma. So here it's forming alpha, our alpha phase. Then we've got a binary eutectic. We've got this phase and another phase, which is darker. That's a hole and the edges are charging. So here it's liquid going to form alpha plus beta. And then here we've got the ternary. We've got 3 phases. We've picked up the gamma, which is the very bright phase. Okay, so we've got the primary phase here, then we've got the binary eutectic there, and then later on we're forming the ternary eutectic there. And that's because different parts of the sample solidify differently. Here's another example. Here's an example of that weak ternary eutectic. Liquid is reacting with alpha to form beta plus gamma. So here we've got dendrites of alpha, and then you've got what looks like a eutectic around it, but this phase is not the same contrast as that phase. So it's 2 different phases. So what's happened is this is reacting, liquid is reacting with the alpha that's already formed. You can see a little bit has been chewed away there to form this, what is now a eutectic. So that's the invariant phase there. The last one, no, this is another example of this one. This is a little bit more complicated, where there was already, this was your primary phase, then you formed another phase peritectically. So this is the beta phase, and now the liquid is reacting with that phase, this very much lighter phase, there it is again, to form two new phases, and I've brought in delta, gamma plus delta. So that's what's going on there. And then lastly, this is the strong ternary peritectic, the one that got wiped off on my slide, where here you've got primary alpha dendrites. You know they're dendrites because they've got a nice periodic structure of a single phase. Then we started to have a eutectic. The liquid was forming these two phases together. And then we've got liquid reacting with the eutectic to form a third phase in here. So that is the strong ternary peritectic, or the class 3 reaction. And then this is another nice diagram. I put this on because we've got ceramics here at the corners. Okay, now I'm a metallurgist and I don't deal with ceramics too much, but ceramics are interesting because they don't normally show much solid solution, and mostly, but not always, when they form phases, they do it in units of the components. So this is a ternary phase because it's got all three components in it, and you'll see it's one calcium oxide, one alumina, and two silica. Okay, here's one that does its own phase. Well, all the ones along here do, but here we've got the units again of the phases. Right, let's go and see what this is looking at us. If you come across the hatch bit there, that shows two liquids. Okay, this, if we look, it's two arrows going away. So we know that between there and there is one of those pseudo binaries. It's behaving like a binary, just that bit between there, not over here. And we know because of this sharp V that this is a eutectic. If you go back to that slide right at the beginning of the binary eutectic, you get a sharp V vertically as well. And then this is a much shallower, so it's more of a kink, and there. So those are peritectic reactions. Okay, there's another eutectic there, and you can piece the things in even if you haven't got the arrows. But this one, you've got the arrows, which is nice. So if you look here, we know that's an invariant reaction because we've got one arrow going in, and well, we know it's an invariant because we got three Liquidus surface meeting. We know it's a ternary eutectic because we've got one arrow going in, two arrows going in, three arrows going in. This reaction here, this invariant of the liquid composition there, it's two arrows going in and one coming out. So it's liquid reacting with corundum or alumina going to form anorthite and mullite. Okay, so you can work your way through that and understand Liquidus surfaces. And then the other thing you can do is you can use the Liquidus surface to work out the solidification sequence. Okay, so as it solidifies. So my composition is X. It's on the anorthite Liquidus surface. So we know it solidifies to anorthite first. And because there's no solid solubility in this, we know exactly the direction that the liquid is going to run. Because it's forming this phase, it's going to run directly away from it. So I've dotted that, and the liquid composition is running down here. All the time, this is being solidified. Then you get the junction to the junction between these two Liquidus surfaces. So now we know we've got a univariant going on. So liquid is going to form in a eutectic pseudo-wollastonite, and more anorthite. How do I know that? Because this is a V. Then it's going to run down here all the time having that eutectic. There it is. Okay, and remember these isotherms are showing a valley. And then it's going to get here, which is an invariant reaction. And there's 3 arrows coming in, one there, and this one, which we've been following. So we're going to get anorthite, pseudo-wollastonite, and tridymite. And on the previous slide, which I forgot to point out, I said that cristobalite is the highest form of silica, and then tridymite is the next one down. Okay, so from this, you can work out exactly the solidification sequence, which is really useful. So Liquidus surfaces are really useful diagrams. And that's it. Thank you very much.